So upcoming announcements, we have a homework due tonight. We will be spending tomorrow's class doing an exam review. So please come prepared with as many questions as you can put down so that we make use of that time, and then we will take the exam on Friday. It's looking like we're going to be actually getting to LL parsing next week. So it is likely that next week I will give people a second option for a project. And that means that I would offer extra credit if you get both projects completed. But you are only required to do 1 out of 2. I will let you choose if you want to do CYK or LL parsing. I think the CYK is pretty significantly easier. But that said, LL parsing is not too bad, so it's a reasonable opportunity to get some extra credit. Other than that, I will be revealing the final assignment either tonight or tomorrow, probably tomorrow. It is the longest assignment of the quarter, but we're also going to have until the very end of the quarter to get it done. But just be aware that projects and the largest assignments of the quarter are coming. All right, last time we ended talking about what kinds of questions we can answer about recursively enumerable languages. And we determined that we couldn't answer very many of them. Even simple questions like, is the language finite? Are there 2 strings in the language that have the same length? Any of those questions are undecidable over recursively enumerable languages, in addition to the membership question. So very little of interest can actually be said about recursively enumerable languages. We were transitioning into this concept of a reduction. We talked about a reduction being a problem that we could reduce down into the halting problem, or some other problem that we had shown reduces to the halting problem, or some other undecidable problem. And this means that proofs that a particular aspect is undecidable about a class of language, we can just reduce it down into the halting problem that says, if we could solve this problem, then we could solve the halting problem. Since we know we can't solve the halting problem, then we know we can't decide this other problem. So we know the halting problem is cumbersome to work with. But we ended last class talking about how we can find some interesting results about context-free languages by analyzing the reductions to the halting problem. So there are some reductions from the halting problem that help us to be able to show these results. So the one we're going to look at as an example is the post-correspondence problem. So the post-correspondence problem says we're going to have a couple of sets of strings. You get 2 sequences of strings over some input alphabet. And we want to find some way to arrange these sequences of strings such that the end result is the same string. So as an example, here we have 2 input strings broken down into 1, 1, 1, 0, 0, and 1, 1, 1. That is the first sequence. And the second sequence is 1, 1, 1, 0, 0, 1, 1, 1. Now the question is there some combination of these strings that produces the same output string? And sure enough, if you look at the first set, we could take the W1 followed by W2 followed by W3, and we would get this same string. And if we took V1, V2, and V3, we would get the same string. So now the question I have is, given an arbitrary set of strings and another arbitrary set of strings, is there a post-correspondence solution? We don't know. The next question would be, is it decidable? That means, yes, if there's a solution, we're going to find it. But are there any sets of strings where the post-correspondence problem is undecidable? Any guesses? Are there any sets of strings where this would be undecidable, where we could answer yes, but we would struggle to be able to answer no? What if these sequences are infinite? Yeah, the strings are, if the sequences have infinite length, then if there was a post-correspondence problem, we would have an algorithm to eventually find one, but we would never finish finding all possible combinations of those strings. We would have no way of knowing if we could find a way to put them together in a way that would work. So it's not possible for all string sets. So we can have a modified post-correspondence problem where we take two initial strings that have to start the post-correspondence problem. And this allows us to be able to represent context-free grammars in terms of the post-correspondence problem. So we have a start state, and we need to start deriving some strings. Then the rule application order, which non-terminals should we go to in order to produce this string, maps to the concept of producing a string out of a context-free grammar. So we can end up making some interesting proofs surrounding what we can and can't do with context-free languages based on this concept of the reduction. So let's take a look at what some of those are. So the first one is, there is no algorithm for deciding whether a context-free grammar is ambiguous. What did I mean by ambiguous? Going back in our notes, what was an ambiguous grammar? Yeah, so we can produce the same string with some different sequence of applications of its productions. So imagine we have a context-free grammar, and the question is it ambiguous? We can answer yes to that question by producing two such parse trees, and then an associated string, and say both of these parse trees generate this string as derivations from this grammar, therefore it is ambiguous. But how would you show that a context-free grammar is not ambiguous? You have to iterate over every string and show that there is no choice at any point about how to derive that string. You can show that for one string, you can show that for 10 strings, you can show that for any finite number of strings, but as soon as the language has an infinite number of strings in it, that becomes a task that will never finish. There's no guarantee that just because you've shown that for every string that you've gone over so far, that there is no string that you haven't seen yet that would have two different ways to map it. We can reduce this to the post-correspondence problem that we just talked about to be able to prove this. Now, note that for particular context-free grammars, this may actually be possible by showing that there's only one possible way that you can move it. Imagine generating an algorithm that takes as input a context-free grammar and determines whether it is ambiguous. That problem in general is undecidable. You may be able to logic your way with a particular context-free grammar. The next one is the intersection of languages defined by two arbitrary context-free grammars. Is that the empty set? So basically, are there any strings in common between two languages? If we represented those languages with context-free grammars, there's no algorithm to figure out whether that intersection is empty. We could say, no, it is not empty if we could find an example of two strings, and we could find a way that both context-free grammars could generate that string. On the other hand, how do we answer yes, it's the empty set? We would just so far have shown that there's no overlap between these two languages and strings that we could generate with this context-free grammar if we enumerated all strings that these grammars could produce. This is also a reduction from the post-correspondence problem. Rather than going into more detail, here are just some more of them, some other conclusions from reduction proofs. So everything that I'm about to describe is undecidable. We have two grammars, G1 and G2, they're both context-free. Are the languages of both of those grammars the same? We just find a counterexample if there's a difference, but imagine that we've been working for 1,000,000 years and every string we've generated from grammar 1 and grammar 2 have been the same. Do they represent the same language? We don't have a counterexample to say that it's no, but we can say for certain that it is yes. At least in general. If we have two context-free grammars, is the language generated by grammar 1 a subset of the language generated by grammar 2? Undecidable. If we have a context-free grammar, is the language of that grammar regular? At least we can't determine it from the grammar itself. Obviously, we could draw a DFA for it to show that it's regular. We could go through a regular pumping lemma to show that it's not regular. But just from the grammar itself, there is no algorithm that parses a context-free grammar and determines whether that language is regular. If we have a context-free grammar and a regular grammar, we can't determine whether the regular grammar is a subset of the context-free grammar. We also can't decide if we have a context-free grammar and a regular grammar, is the intersection of those grammars the empty set? So lots of questions about context-free grammars that we can't actually answer, at least in general. If we have one particular grammar and we want to answer this about that grammar, we can logic about that grammar using the exact rules of that grammar. But we cannot generalize this to write an algorithm that takes as input arbitrary grammars and answers yes or no. Does that difference make sense? I think that's a very important distinction, because I think intuitively you might think, I would be able to do this with a particular grammar, but the rules that would help you to do that for that grammar aren't applicable to every grammar. So we can't generalize that into a program. All right, there's one more really important aspect to talk about, which is the efficiency of Turing machines. This is the last element of our kind of very broad, vague theory of computation set of slides before we dive into compilers. But let's talk about efficiency. So we've only really talked about what's possible and not possible, or what's decidable and what's not decidable. And we've not talked at all about how efficient our Turing machines are. As we know with our own programs, you can write different programs that solve the same problem that have different complexities. This is true for Turing machines as well, because a Turing machine is just an abstracted computer. So depending on the Turing machine program that we write, it will take different amounts of time to be able to determine the answer, yes or no, assuming the problem is decidable. As an example, the efficiency of deciding A to the n, B to the n on a single tape Turing machine. I think I spoiled this to you in office hours yesterday, Logan, I think. Or maybe I spoiled it in class. My memory is that of a goldfish. So you can get an order for this by thinking about, let's start with how did we solve this problem? What were the steps? So we started out by mapping a single A to a single B. So, I mean, let's say we have on our input tape, we have some A's and some B's, and we want to determine if these are if this string is in the form A to the n, B to the n. So our read-write head would start here. We would turn this A into an X. I guess we need an extra one at the end here that's a blank, just to be sure. And then we would move all the way right until we found a B. We would turn that B into a Y. And we would move back until we saw an X, and then move back to see an A. We would turn that A into an X. We would then move until we saw a B. We would turn that B into a Y. We would move back until we saw an X. We come back to an A. We turn that into an X. We move all the way to the end. See a B, turn that into a Y. Move all the way back till we see an X. Move right. See that this is not an A. It's instead a Y. So now we transition to a new state and we move past all of the Y's, and we want to ensure that the element to the right of the last Y is that blank. Once we do, then we accept. So the question I have for you is, how does all of this work scale as we add more X's and more Y's to this A to the n, B to the n? Can we place an order on that much work? You could think of it in terms of, okay, how many steps does it take to verify a single A and a single B? So if here, n equals 3. So to verify a single A and a single B, we had to see this as an A, move, move, move. That's 3 steps. Check if this is a B, move, 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 move back. So we had something like 2n plus 2 to verify a single A and a single B. How many of these are we going to need to do? 3 of them. So we end up with 6n squared plus 6, something like that, 6n, that's 6. We have 3 of those, so I guess we're at 6n plus 6, which when you scale this, how is this process, what is this coefficient doing? It is a squared term. Because what would change here is this value would change and this value would change. If you needed to multiply this by 4. So we end up with, let's reveal 2n moves matches a single A with a single B. We can drop off the +2. So we get complexity n squared. Because we need to do that n times, right? So this really isn't 3, it's n. Sorry, so n times 2n gives us 2n squared plus 2n. That's better. So the dominant term here is the n squared, so this is quadratic. But now, what happens if we do the same problem on a 2-tape Turing machine? If we have the ability to store some information as we go, rather than having to move the read-write head all the way to the end, and then come back, how does that let us change the problem? Well, we have a these could be A, B, B, and a blank at the end. And now we have a second tape that we can use. So how do we know that this is A to the n, B to the n? Is there an algorithm that is more efficient than something that's quadratic when we have a second tape to write? I'm also going to draw an extra space over here that's a blank. We can just map, do something like, all right, read an A, write an A, read an A, write an A, read an A, write an A. Now we start reading B's. So now instead of moving left across this tape, sorry, right across the tape, we're going to move left. I'm going to do something like, all right, when I see this B, I expect to see an A here and nothing else. So this B is going to map with this A. This B is going to map with this A, and this B is going to map with this A. As I move right and see a blank here, I should move left and see a blank here. If I do, then this is the form A to the n, B to the n. Does that make sense? What complexity does that have? That is in fact linear. With a single pass, left to right, across the A to the n, B to the n, we can determine that it's in that form based on the extra scratch tape that we have here. With a single Turing machine, we could still do this work, but we would have to be moving all the way past, all the way back, all the way past, all the way back, all the way past, all the way back. So that turns something that's quadratic into something that is linear. So just like with programs, you can see that Turing machine efficiency is an important question if we care about how long something is going to take and not just whether it's possible or not. But note, what we did here is we added some parallelism to the program. So you can imagine if you have extra CPU threads, rather than waiting for some things to finish, or if we want to be able to store some extra information, we could easily parallelize and see that we can reduce the time complexity of a problem by storing some information as we go. Questions on anything we've covered so far? All right, that brings us to the end of our discussion on the theory of computation. Hopefully this was somewhat enlightening, trying to tie what we do and how we write algorithms to this concept of what is solvable and what is not. So we're going to transition from here into finally talking about compilers. Because now we have all of the background work that we need in order to talk about how compilers work. It turns out that compilers use just about everything that we have talked about so far in some portion of their construction, which is why we can't just start talking about compilers and writing a compiler in a 10-week course, because it's going to rely on a lot of the information that we've covered so far. So the name of the course was compilers when it really should be automata and compilers, because we can't do it without this. So let's start with just what is a compiler. We've talked about it in class, but a compiler just translates high-level program into either assembly or machine code. So we need some translation algorithm. A lot of you have been working with Java in most of your classes here. So the ability to translate Java code into either some kind of bytecode. So that's how Java works. It translates it into Java bytecode, and then Java bytecode is interpreted at that level to be turned into machine code. Because the machine code is different across different architectures. So you may have an x64 architecture, you may have a MIPS architecture, depending on the exact architecture of your system. You will need to translate that bytecode differently. But the idea is that Java, there's a single translation between Java and bytecode, and then you just write these separate translation algorithms from bytecode into the associated machine code that is run on your particular architecture. However, other languages have a slightly different approach where they translate directly into assembly or directly into machine code. The basic idea is that if we had to write in that machine code, we would never get anything done, because it is not how we think. As humans, we think in language. We think in higher level logic. We do not think in lower level logic. High level languages that we actually write in are gibberish to a computer because it only operates on low level instructions, and low level instructions are gibberish to humans. Even if you write in an assembly language, there is still an assembler to convert it into machine code. So what the computer actually executes is always the machine code, the actual binary instructions. But we need a way to get from what we write to that. Machine code, of course, is also platform dependent. This makes sense. If you run an executable on Windows and you try to run that same executable on a Mac, it will not work. An executable in Windows is the actual instructions. And I already talked about bytecode rather than write compilers for every possible endpoint. So you can imagine needing a different compiler to convert Java into something that's executable in Windows, and Java that is executable in a Mac environment or a particular Linux distributions environment. We can instead compile them into bytecode. Bytecode is platform independent, and then the bytecode is run on some kind of virtual machine, and the virtual machine does that last step, converting the bytecode into the associated machine code that runs on that machine. So That is how Java works. So let's start with this brainstorm. You're in charge of designing that process. You need to take as input a Java program, and you need to produce as output this intermediate bytecode that is as close as possible to machine instructions that makes the work of that virtual machine as easy as possible. What steps, general steps, would you take? Don't think about writing the whole algorithm for what that is done. But if you had to create some English words or use some English words to describe the aspects of that process, what would you imagine that process entails? So to give you an idea of where to start, the first step of this would be we need to take the input of the program and break it down into something that is readable. Something where we can say, what is this? What is it? So we call that the scanner. And it maps to exactly what you used a Java scanner for, is it's going to read tokens. It's going to break down a program into an associated number of tokens. Each of those tokens represents what you might think of as an English word or a piece of a word in a Java program. We feed those tokens into a parser. The parser now needs to determine whether these tokens map semantically into meaning. So we're going to create a parse tree, just like we have for our grammars. And we're going to now be able to make kind of instructions out of these tokens. We then need to pass this into a type checker. The main goal of the type checker is to ensure if an expression is supposed to evaluate into an integer, that we're trying to put it into an integer. Something like this. The type checker makes sure that what we are trying to put into an integer shaped hole is in fact an integer. What we're trying to put into a character shaped hole is in fact a character. From there, we take the parse tree with the verified types, and we can generate some intermediate code. This is some code that's not necessarily in Java anymore, but it's something that can now be optimized. So we're going to make a pass through this intermediate code, and we're going to say, can I do any of these things faster? So this goes through a code optimization process. Once the code has been optimized, we generate the new code in the target machine language. So we actually go through the conversion process because we define that conversion process. So once we ensure that this code adheres to the rules of the language, we can then apply the translation rules to that code to generate the target machine code. So we're going to go through this process in just a little bit more detail for each one of these steps. But just giving you an overview of exactly what the entire process looks like before we dive down into some of the details. So tokens and scanning. We have a scanner program that is going to identify these tokens. A token is just some number of characters surrounded by white space. Each token is going to be assigned a particular type. So we may have an integer token, we may have a keyword token, we may have a variable token. But each one of these tokens has some kind of type. If the user hates white space, then we may need to analyze each token. So you can imagine something like this as being a line in a Java program. This user hates spaces, and there are multiple tokens here. So we would need to analyze this stream of text and break it down into its tokens. So sometimes white space is optional. We end up with a list of tuples. The first element of that tuple is the token itself, and the second aspect, the second element of the tuple is the type, the integer, the keyword, the variable, etc. And it's passed to the parser in the order they appear in the program. So you can imagine now breaking down a program into a list of these token type pairs and then passing those on. That is the entire purpose of the tokenizer, the scanner. Let's give you an example. What are the tokens and types here? We have sum, which would be a variable. Since it's not a keyword, we would do a lookup and say, all right, this is text. Is this text a keyword in this language? No? All right, it must be a variable. Great. We have the equals. That is a mathematical operator. Or the assignment operator. We'll go with that. So we could assign this to be the assignment operator. Then total is another variable. Plus is a math operator. And 10 is an integer constant. So we would split this line down into those associated token and type, that token type pair, and then we would ship them off. That says we've identified which types each of these tokens are. In the second line, green is not a keyword, so it is a variable. If is a keyword, we're not allowed to make a variable called if. It has a particular meaning in our programming language. 6.5 would be a double constant or a float constant, and 87 would be an integer constant. Note that nowhere in here are we doing any kind of syntactical analysis. We have no idea if either of these statements are valid or viable in the associated language. We are just tokenizing it at this point. It's the job of the parser to figure out whether these tokens have meaning. Questions on tokens and scanning so far? At least as to what it does and how it works. If you do end up with questions, it'll be easiest, especially since everyone is remote right now, if you type yes and then type your question, because that will tell me that a question is coming. And that way, if I don't get a yes within a few seconds, I can move on. All right, so how would we code up one of these? How could we make a scanner? Thoughts on this? How could we implement a scanner? The key idea that leads back to what we've talked about is that we could use a DFA for this. The DFA would be able to recognize all valid tokens in a particular programming language. Final states would recognize different tokens, and you would read in each token until a set of tokens is identified as a label of interest. As we reach that label of interest, that is a final state. And we could then pass that set of tokens on to say, this is a statement. We could also build a regular expression for each valid token. Something that says, all right, variables all start with a lowercase letter or an uppercase letter, but not a number. We can make a regular expression that maps to that and says that this token is a valid token. Is there any valid Java token that's something like 1A at 6? That doesn't map to anything in the Java programming language. So we need some way of saying this is not a token. So we would have either a DFA or a regular expression that would allow us to say this is either a valid token or an invalid token. For every token that we find in the program, compare it to the regular expression until we find a match. And now we can say, all right, all double constants look like this. So we could run it through the double constant DFA or the double constant regular expression that says, is this a double constant? Note that we did this in one of our past homeworks, where we tried to come up with a list of rules, a grammar, for a double precision floating point number. You could do this with a regular expression as well, just like you could do it with a grammar. So we want to ensure that each of these tokens map to what type they are. So we have different regular expressions for the different types, so we can compare them to figure out what type they are by passing them through all of these DFAs or regular expressions. So regular languages map to this concept of a scanner and tokenizer, because we can recognize different aspects of strings that way. It's basically just a string search, trying to map it to a particular type of string. Things get a little bit more difficult when we get to parsing. So any questions on scanners or tokens before we move on to parsing? All right, so the next step we're gonna get to is parsing. Now we have this list of tuples coming into this, so the tokenizing is done. And we now have this stream of token type pairs. We need to match this to some context-free grammar that represents the programming language. One of the very first classes in here, we looked at the Java language grammar. So now we need to have built some kind of context-free grammar that matches the syntax of the programming language. The goal of the parser is to determine whether this stream of tokens has meaning, which means that we're going to be starting at some start state in the grammar, and eventually we could try to match that grammar and say, can this grammar generate this program? If it can, then this program is in that language. If we can't, there is some kind of syntax error. This string that we have written is not in Java. So we use the grammar to attempt to derive the program from this stream of token type tuples. If the program can be derived, it is syntactically correct in that language. And then we can build a parse tree that shows exactly how that was done. The parse tree is the exact rules that were used in that grammar to generate that program. When we recognize that rule, we make a new node at some location in the tree. And we say, all right, we derived these non-terminals from this list of tuples. If we're syntactically correct, the tree is complete. And the tree represents, it's an internal representation of the program in terms of the grammar. When this process is complete, we just send on that parse tree to the next step. So let's get an example of what parsing might look like. Here we have a language. The language is a very simplified programming language. We need a main method made up of a sequence of statements, each of which must be an assignment or a print function. So here is a program. We denote that it is a main, and then we have some assignments and a print. Let's go ahead and spend a little bit of time writing a context-free grammar for this language. You want to use the following non-terminals: program, sequence, line, variable, integer. So give this a shot. So those are the non-terminals, but now see if you can generate a context-free grammar. Remember that we have non-terminals and we have terminals. Terminals are just tokens that are not part of the non-terminal. So maybe I'll give you the first line. We know this starts with the concept of a program. So every program must be defined in terms of, we say that we get this main. So we expect to see this token main. It's not a non-terminal, it's a terminal. We expect to see this string followed by a space, followed by this string, followed by a space, followed by this string, followed by some sequence. So this would be your first rule in that grammar. Every legal program in this language starts with main followed by some sequence of lines. So break down this into the associated rules. Go ahead and give that a shot, and we'll probably have to come back to this tomorrow for an answer, but spend the last couple minutes of class working on this. Anyone have any questions or trouble getting started? If you think you have a definition for sequence, let me know. I'll write that one before the end of class. Any guesses for what goes here? The purpose of this non-terminal is to make programs be able to be arbitrarily long. We don't know if this program is going to be 1 line, 4 lines, 1,000,000 lines. That is extremely close, Dan, extremely close. We would have infinite recursion and only allow for a single line if we only have a sequence by itself. So we need to pair. We can either terminate this by saying exactly as you wrote, a line. This would say this is the last line of the program. Or we want a line followed by a sequence. So this would allow us to say, if we're not at the last line of the program, we can define the next line and say there's more program to come. Or if we're at the last line, this sequence becomes that last line. So this allows us to make an arbitrarily long program by recursion. So we will end there for today. I'll come back and reveal the rest of this at the start of class tomorrow, and hopefully there's at least one person in class. See you for that, unless you have questions.